All right, let's get right into it. Today, we are taking a journey to answer a really, really fundamental question. What is everything actually made of? We're going to dig into the structure of the atom, the tiny building block that makes up you, me, and literally the entire universe. So let's start with a big one. Just look at your hand for a second. It seems pretty solid, doesn't it? But what is it really made of? If you could just keep zooming in, way past the cells, past the molecules, what would you find at the very bottom? Well, the answer to that actually starts thousands of years ago. So way back around 400 BC, the ancient Greeks had this idea. They imagined that if you took anything, a piece of wood, a rock, whatever, and just kept cutting it in half over and over again, you'd eventually hit a point where you just couldn't cut it anymore. They called this final, tiny particle an atom, the basic, uncuttable piece of everything. Now, for centuries, that's all it was, really. A cool philosophical idea. But, as science started to ramp up, that whole uncuttable concept was about to be seriously put to the test. And what we found out would completely change how we see reality itself. All right, first up, the uncuttable atom. So let's start with how scientists first thought about it. For a long, long time, the idea that the atom was just a solid, indivisible little sphere was the bedrock of modern chemistry. Okay. So after the Greeks, the whole idea kind of just sat there for ages, until 1808. This guy, John Dalton, he comes along and proposes the first real scientific theory. He pictures atoms as these tiny, solid, billiard ball-like things. And his theory was amazing for explaining how chemicals react. But toward the end of the 1800s, scientists started seeing some really strange results in their experiments, things that just didn't make sense with this simple model. And this is where things get really interesting. This is the moment scientists figured out that the atom wasn't a solid little ball after all. It had pieces inside. They were about to crack it wide open. So the first real clue came from this piece of equipment called the cathode ray tube. It's really just a glass tube with almost all the air sucked out of it. And when scientists passed a high voltage current through it, they saw this mysterious beam, this glow, that flowed from the negative end to the positive end. So what did they figure out from these experiments? Well, they saw that these mystery rays were made of particles that had a negative charge, and you could actually bend the beam with a magnet. But here's the kicker, the really mind-blowing part. It didn't matter what the tube was made of or what little bit of gas was left inside. They always got the exact same particles. What this meant was, wow, they'd found something universal, a fundamental piece of all matter. They had just discovered the electron. And that supposedly uncuttable atom? Yeah, it had just been cut. Okay, so now we have Thomson's pudding problem. If atoms have these tiny negative bits floating around, what does the rest of the atom even look like? Well, the first guess was, let's just say it was a bit like a dessert. So J.J. Thomson, the guy who discovered the electron, he had a puzzle on his hands. He knew that atoms overall are electrically neutral. So if they have these negative electrons in them, there has to be some positive charge in there to balance it all out. His best guess became known as the plum pudding model. The idea was actually pretty simple. The atom was this sphere of evenly spread out positive pudding, and the little negative electrons were just kind of stuck in there, like raisins or plums. It was a pretty clever model, right? It totally explained why atoms are neutral. But it made one huge assumption, that all the positive charge and all the mass was just smeared out evenly. And that assumption was about to be tested in a big way. And that brings us to Rutherford's nuclear revolution. Yeah, that assumption. It was about to be completely blown to pieces by one of the most famous experiments in all of science. So, Ernest Rutherford and his team wanted to test this plum pudding idea. The plan was this. They were going to shoot these tiny, fast, positively charged things, they're called alpha particles, at this incredibly thin sheet of gold foil. I mean, it was only a few thousand atoms thick. So, what were they expecting to see? Think about it. If the atom is just this soft, squishy pudding of positive charge, then shooting an alpha particle at it should be like firing a cannonball through a fog bank. They expected the particles to just zip right through, maybe getting nudged just a tiny bit on their way. But what they actually saw was just unbelievable. I mean, sure, most of the particles did go straight through, exactly as they predicted, and some of them were deflected a little bit, but, and this is the part that changed everything, a tiny, tiny number of them bounced almost straight back, as if they'd hit a brick wall. I mean, we have to put this in perspective. It was only about 1 in every 20,000 particles that did this. Rutherford himself said it was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. There was only one way to explain this. For a positive alpha particle to get knocked backwards so violently, it must have run into something incredibly dense and also positively charged. The whole plum pudding idea, totally wrong. All of the positive charge and almost all of the atom's mass had to be packed into a tiny, tiny point right at the center. And this is where you really get a sense of the scale of the atom. It is almost entirely empty space. The nucleus is so unbelievably small compared to the rest of the atom that if you scaled it up to the size of a cricket ball, the edge of that atom would be about 5 kilometers or 3 miles away. Just think about that. Okay, on to our last section. Light, energy, and what's next. So Rutherford's experiment gave us this new picture, the nuclear atom. A tiny, dense, positive nucleus with electrons orbiting it. It was a complete revolution. But, and there's always a but in science, right? This amazing new model had a huge, glaring problem of its own. You can picture Rutherford's model like a mini solar system, with electrons as planets orbiting the nucleus sun. But here's the fatal flaw. According to the laws of physics they knew at the time, an orbiting electron should be constantly giving off energy. And as it loses energy, it should slow down and spiral right into the nucleus in a tiny fraction of a second. Basically, every atom in the universe should just collapse in on itself almost instantly. But, I mean, look around. They obviously don't. So something was wrong with the physics, not the atoms. The world exists. The next clue to solving this new puzzle didn't come from particles, but from light. See, scientists noticed that when you heat up a gas of atoms, they don't just glow like a light bulb with a full rainbow of colors. Instead, they only give off light at very specific, sharp, individual colors. It was like the atoms were sending out a secret code, a message that hinted at why electrons weren't spiraling into oblivion. And so that leaves us with this incredible, mind-bending question. We've gone from thinking the atom is a solid, uncuttable ball to realizing it's almost entirely empty space, like a tiny solar system that, by all rights, should instantly destroy itself. So how does anything hold together? How does anything exist? Well, the answer to that would require a brand new type of physics, quantum mechanics. But that's a story for another time.